Okay. Hi guys, I am Su Cheng, and today I'm creating this physics video to help you all with your physics. So, this is just the first video in a series of physics videos I'm going to make, and please note this is just going to apply to secretaries. Okay, so the reason I wanted to create these videos was because in term 3 we had a common test, and as you may know, the performance wasn't too good. So I wanted to create these videos to help you guys understand the physics concepts and stuff better, and hopefully we'll be able to score better in your physics. And so let's start. So the first topic I'm going to be talking about today is vectors. Okay, and first I'll first be covering the concept, and then I'll be covering how to do vector resolution. Okay, so here it is. Okay, yeah, so first I'm going to explain what a vector is. So what is a vector? First you have to understand what a scalar is. Yeah, okay, so a scalar is basically something with magnitude only. So for example, here's a line, uh, the line, and so yeah, so here's the line, and here's a scalar, and let's just say it has a magnitude of 5. So a vector is different from a scalar in the fact that it not only has magnitude, it also has a direction. So um, basically this is what a vector will kind of look like. So you have a line. Not only do you have a line, you have a direction, basically where the vector is supposed to be pointing. So in this case, it's pointing to the right, and let's just say it also has a magnitude of 5. Okay, so the magnitude is basically how long the scalar or vector is. So for example, if this is 5, you can have a longer uh, vector or scalar, and its its magnitude can be uh, say 7. Okay, so a vector has a direction also. What that means is that the magnitude of so that means a vector can also take on negative quantities. So if the if this vector is has a magnitude of 5 and is pointing in this direction, a vector that is negative 5 would have the same magnitude, uh, like this. Okay, okay, yeah, like this, and it will be pointing in the other direction. So if this vector is 5, um, and this vector would be negative 5. Okay, so notice, so here we define um, this direction to be the positive direction. Okay, so this is the positive direction. So yeah, and also, so note that you can define any direction to be the positive direction. So let's say you define this to be the positive direction, then uh, so this vector that this have a magnitude of, let's say, a, then this vector, which has the same magnitude but a different direction, will be with a value of uh, negative a. And note that the magnitude of a vector is always positive. It's kind of like the absolute value. Okay, so you can define any direction to be a positive direction. So you can also define it like this way, or you can define it the other direction, or basically any direction you want. Okay, so that's the basic concepts explained. Yeah, so I'll now be moving on to vector resolution. But never mind. Yeah. Okay, control V. Uh, okay, so for for vector resolution, it's basically like finding the sum of two vectors. So let's say you have this vector and you have this vector, and you want to find the sum of these two vectors. So what you will do is basically you make sure that the end of one vector is the start of another. For example, for these two vectors, this is what the resultant vector will look like. I use blue. Yeah. So this is the resultant vector if you want to add these two vectors up. And so you have the direction of the vector, which is this way. But what about the magnitude? So the magnitude is basically all this is a vector diagram, and all vector diagrams are drawn to scale. So you measure the length of this. So if you know the length of these two, and assume they are drawn to scale, so you can using that scale you can also measure the measure the magnitude of this vector and yeah know what its magnitude is. So for example, this could be, don't know, 7. This could be 4. This could be 7. This could be 4, and you can measure this and find out its magnitude is, let's say, 9. Yeah, so that's how you add up two vectors. But this type of addition is called arithmetic addition. But for this, but then for this type of addition, no, so in this case, all you need to do is connect this point to this point, because the start of one vector is the end of another. However, you can have another case in which you have two vectors, first vector here, and then the start point of the other vector is also the start point of the first vector. So how do you resolve these two vectors? So what you do is sort of like parallelogram rule. So okay, so maybe you may not understand what the parallelogram rule is, but I'll just let me explain first. So it's basically right. You mm, you take so for example so this vector stay here. You move this vector over to the other side such that its start point is the end point of the first vector. Yeah, something like this. This is supposed to be a dotted line, and so the resultant vector you can obtain by connecting these two points. So it's kind of like if the start point of one vector is not the end point of another, make it that way. So alternatively, instead of moving this vector over here, you can move this long vector over here instead. So it'll kind of look like this. Uh, yeah. So notice this. Notice that. Notice that no matter whether you move this vector over here or this vector over here, the resultant vector is will always have the same magnitude and direction. So this is kind of because this whole the shape formed the black lines is kind of like a parallelogram because this line is equal to this line and this line is equal to this line. So this whole thing is like a parallelogram. So using a so this is why it's called like parallelogram rule. So if you want to resolve two vectors emanating from the same point, this is how you resolve two vectors. Also, note that you can also to when you resolve vectors, you don't always need to resolve only two. You can resolve three at a time. So for example, uh, these three. So if you want to refine the resultant vector of these three, it's basically um, you set one vector to stay as it is. Let's say the top one over here, and you pick a second vector to move to the endpoint of this. So let it be this vector. So I'm going to move this vector over here. Yeah. So yeah. So this is the second vector of the movement. Okay. So after that, you move the third vector to the endpoint of the second vector, like this. Yeah, like this. So the resultant vector will be basically connect the start point of the first vector to the endpoint of the last vector, and this is the resultant vector or resultant force. Okay, yeah. So this is the resultant vector. Oh yeah, and one more point I forgot to mention. Note that resultant vectors are normally marked with two arrows instead of just one. Yeah. So this is the resultant vector. This also is the resultant vector. Let me mark it with another arrow. Yeah. So so this is how you resolve vectors. But what if the special case? What if you have, let's say, three vectors? Um, three vectors, and like this, one, two, and three. Let's say you have three vectors like this, and you try to resolve them. So resolve them like this. first, and then you move the third vector. However, what if you find that the endpoint of the last vector ends at the start point of the first vector? So this is kind of like a closed loop. So what it basically means is that the resultant force, the resultant vector is 0. Yeah, so the resultant force is 0, the vector. So what this means is that system is in equilibrium. Yeah, so the system is in equilibrium if all the vectors, when you resolve them, end up at the start point again. So what it means is that, let's say these are three forces pulling on a ball in the center. What this means is that the ball will not move, as the three forces acting on the ball are in equilibrium, will cancel each other out, and the system is set to be in equilibrium, right? Okay, so yeah, so wait, is there something? Okay, so um so right, in question normally in questions may be asked to so so let this be you may be asked to resolve two vectors and find the resultant force. This is basically what I told y'all, what I explained to y'all just now. Use the parallelogram rule. Just move this vector here, and this is the resultant force. So the question may have a second part, which asks you to find a third force or vector acting on the system such that this whole thing is in equilibrium. So what is this third force? Answer is, it's basically just the the vector has the same magnitude, but the, op, the opposite direction of the resultant force. So wait, uh, this is the resultant force. So yeah, so um, let's say it has a magnitude of, I don't know, r. r. So the magnitude of this third force. Wait, what? Uh, the magnitude of this third force will mm, be r as well. But note that it is in the opposite direction. So vector itself is negative r. Yeah, let me fill this in first. So this is the third force that will act on the system to make it be um, equilibrium. So why is this so? Because like to don't consider the individual vectors first. Consider the resultant vector. If you if you want a if you want a vector that can balance the whole system, it means that when you resolve um it means that when you resolve all the vectors, the last vector should come back to the point where all the vectors started, where the first vector started. So basically, like, right, this third force will cancel out this third vector will cancel out the resultant vector of the other two or so vectors, and since they cancel each other out with the same magnitude and opposite direction, the forces or vectors or whatever will return to equilibrium here. Okay, so uh, that is vector resolution explained, and I'm done with vectors. Yeah. So yeah. Forget it. Um, excuse me as I so wait. Uh, okay. So the next topic I'll be explaining is kinematics. Kinematics. Yeah. Okay. And so I'll be covering three things in this topic. The first thing is the termi terminology. The second thing is the terminology. The second thing is the equations, and the third thing is graphs. Yeah, here. So first, I'll be explaining the terminology. So so you might remember. So the quantities in kinematics can be split into two basic groups. Groups: the scalars. Oh my God. And the vectors. Oh my God. Excuse my handwriting. Okay, so uh, the scalar quantities in kinematics basically um, basically what you have learned in your P6 math. So it's like you have so let me just use this. So it's basically speed, uh, and distance. Yeah, and there's one more you learned, time, but it's not included uh, in this table. So in Sec 3 you learn new quantities, vector quantities. So these vector quantities will mostly have corresponding scalar quantities. So it's like each scale, so speed and distance, they'll correspond to a specific vector quantity. So so speed corresponds to velocity, velocity in um vector as a vector quantity, and distance corresponds to displacement um in as a vector quantity. And so um there's one vector quantity that doesn't have a corresponding scalar quantity, and that is acceleration. Here it is. Yeah, and wait, let me add something. Yeah, So I've kind of explained the difference between scalars and vectors here, scalars and vectors just now, but I'll just kind of explain the difference between these two. So basically right, um, basically, let's say you have a road, and let's say you have a car traveling on the road. So first, the car travels for um the car travels for 7 kilometers forward, and then reverses goes back for uh, 5 kilometers. So what is the difference between the so what is the total distance and the displacement? So the distance is basically you add up all the quantities. So distance is basically a scalar, so you consider the magnitude only. So the distance equal so b equals 5 plus 5 plus 7 equals 12. Yeah. So what about the displacement? Displacement is a vector quantity, so you must also take into account the direction. So wait, how to define the positive direction? So let this be the positive direction. Okay. So displacement here is not 7 plus 5 km. 7 plus 5 km. It's actually 7 minus 5 km because here the 5 km as a vector quantity is actually negative 5 km. So because right the 5 is going in the opposite direction, positive direction, negative direction. So S equals 7 minus 5 equals 2 km. Okay, yeah, so this is the displacement. This is the difference between distance and displacement. And you can so with this you can kind of understand the difference between speed and velocity and acceleration and stuff. Yeah, okay, so one thing to take uh, mm, okay, never mind. So yeah, so now I'll be moving on to the equations. Okay, wait. Okay, so now I'll be explaining the equations. So there are 4 equations you need to know in kinematics, and oops. So the first, wait, I forgot. Okay, so um, so yeah, so let me add the new terms here first. This is just in SI unit. This is an SI unit. You can have like km per hour and stuff, but just stick to SI units. Acceleration. The acceleration is uh um know that acceleration is meter per second square. Okay, like that, something like that. Okay, so I'll be explaining the equation. So there are four equations you need to know, and so I'll start with these two. V equals U plus AT, and S equals half U plus V E. I'll start with these two because these two are like the the base equation. They don't need to be derived. So it's like it's like from these two you derive the other two equations. The other two are derived equations. So I'll go through these two first. So know that U is means the initial velocity and V means the final velocity. So the base equations. So I'll be explaining the first equation, V equals U plus AT. Um, so this is to kind of make sense to you as like let's say I don't know, uh, so let's say you have a car going at you have a runner running at 5 meters per second, and he accelerate each second he accelerates by 1 meter per second square. So 1 second later he will be 6 meter per second. His velocity will be 6 meter per second. 2 seconds later is 7 meters per second. 3 seconds is 8. 4 seconds is 9, and so on. Yeah. Okay. So now we're explaining the second equation. So the second equation is S equals half U plus V T. So this is basically saying you can interpret on your own. Mind. So what this means is, so it's like, let's say you have so let's say you have car A. So car A, it travels. So is at first its velocity was 8 meter per second. So it traveled with an acceleration of 1 meter per second square, and eventually 4 seconds later it reached the speed of 12 meter per second Yeah. Then on a so then you have another car B. Then right, 4 seconds. Yeah, so you have car B. Looks very bad. Yeah, so it basically travels for 10 meter per second throughout the whole 4 seconds. So in the 4 seconds, which car travels more distance? The answer, they travel the same distance or displacement. Actually, in this case, both are the same since the direction is the same, but whatever. So why is it that these cars travel the same distance? So you may have learned before in your primary 6 math, total speed, I mean total distance divided by total total uh what's it, the total time you can get by dividing this. You can get the total, I mean wait, not the total, the average speed, the average speed. Oh my god. Yeah, so you can get the average speed. So um so so here you will notice that the total time is the same, and average speed, notice that here we're assuming constant acceleration. The average speed is 8 plus 12 over 2, which is 10, and for car B the average speed is also 10. So you'll find that the total distance is this times this, which is both on the same. So the total distance traveled for both of the cars is the same. Okay, so it's kind of like, let's say car A was traveling slower at first. So whatever distance it lagged behind car B by in the first few seconds, it will like make up for it in the last few seconds. You can kind of see it that way. So that's the second equation explained. Yeah, so I'll be so I'll be deriving the other two equations. So now I'll be deriving the third and fourth equation. So the third equation is S equals ut plus half a t squared. Uh, yeah. So and the fourth equation is v squared equals u squared plus 2as. Yeah. Oops. These two. Yeah. Okay. So these two are derived equations because they cannot be directly like understood because they are derived from, with these two as the base equations, you derive these two and derive from these two. So so let me derive the third equation first. So the third equation is derived like this. So equals u plus at. You notice that you can sub this into the v here. So s equals half u plus vt equals half u plus u plus a t t equals half 2u plus a t t, and you expand this thing, you get ut plus half a t square. Yeah, so that's this equation derived, and so now derive the fourth equation. Okay, so the fourth, wait, let me erase this first. So the fourth equation is basically you have the okay, so the fourth equation, the first step is to derive it. The first step is squaring the first equation. So v squared equals u plus a t squared. So extend right side using the formula a plus b squared equals a squared plus 2ab plus b squared. So you expand this, you get v squared equals u squared plus 2u a t plus a squared t squared. Sorry, that's bad handwriting. So you combine the last two terms, you get u squared plus let's see 2u equals at. You factorize the last two terms, 2u plus a t. So you have this. You will notice that this 2u plus at is also your u plus v, because v equals u plus at. So this will be a u plus v t is equal to u squared plus 2a square bracket half u plus v t, and you notice square bracket contains your s, so v squared equals u squared plus 2a s. So there you have it. So wait, let me erase this first. Okay, so so why do so you may be thinking, why do we have four equations? Like, why can't we just have like one, and like let's say these two, and derive the others and use algebra to derive the others? So what you may notice is that all these, never mind. So basically what you may notice is that all these all these equations are missing a certain quantity. Five quantities P, U, A, P, and S. So you may notice this is missing S, the displacement. This is missing A. So this is missing V, and this is missing the T. So it's like in the question you must identify all the quantities. You will try to identify all the quantities, and basically there's always going to be some quantity that's missing. So from the quantity that's missing, from here you can select the most the best equation to use that does not have the missing quantity that you do not need to calculate, and just um, do it. Yeah. So you may be thinking, is there some equation that has u as the missing quantity? The answer is yes. So first, you must rewrite the first equation as u equals v minus at, and you sub that into the second equation. You can get s equals vt minus half at square. Yeah. So let's rearrange these equations and write them here. Okay, so here you have your 5 equations, and notice that I've rearranged them. So for the exam, you only need to know of the first four. The fifth equation is just extra. So now we'll be moving on to graphs. Okay, so graphs. There are 3 graphs you need to know. The first, oops, okay, the first graph you need to the first type of graph you need to know is the velocity, the displacement time graph. Drawing not very good here. Yeah, so this is s meters, displacement in meters, and p in seconds. So you can have a graph going like this. Yeah, and so note that this point is supposed to be a sharp turn. So let this be 4 seconds, 6 seconds, and 8 seconds. So let the speed here, the displacement here be uh, 8 meters, for example. Displacement here, let it be 16, for example. And yeah, So what it means here is like, let's say this is the displacement time graph of a car traveling on a road. So here's a point. So this is the, let this be the road. So this is the point when uh s this is the point when s equals 0, or it's like the origin. So for 4 seconds, the car may be like here, 8 meters away from the origin. 6 seconds, it may be here, 16 meters away, and 8 seconds is just back here. Yeah, so that's how to interpret a displacement time graph. So the next graph you need to know is the velocity time graph. Okay, here is, so it could look something like, I don't know, this, like this. Okay, let me draw it better. Yeah, so 2 seconds, 4 seconds, and 8 seconds. This is 12, let this be 12, let this be 16. Okay, just let it be like this. And wait, okay, so yeah, moving back to the displacement time graph. So note that for the displacement time graph, for displacement time graph, the gradient of displacement time graph is gradient is basically the velocity. This is because velocity is like the rate, the change in displacement over change in time. So it's the velocity is the gradient. Okay. Yeah, so moving back to this velocity time graph, so it basically just says velocity of the car at different points in time. So positive gradient means the car is moving forward in the positive direction, and a negative gradient means that the car is moving at the negative velocity and is moving backward. So for the uh, velocity time graph, the gradient is acceleration. The gradient, wait now, I'll put this here. Okay, put it here. The gradient is the acceleration, as the acceleration is change in velocity over change in time, and the area under the graph is the displacement. So yeah, so it's kind of like you can yeah. So if this is because like if you compare it second by second, you can kind of understand like it's always the average speed and stuff. So okay, wait, I'll just explain it like this. So let's say in the velocity time graph instead looks like this: a constant velocity at 14 meters per second. It will basically be traveling the same distance since you have the same average speed of velocity. Notice the area under the graph is the same as this region equals this region. And also you can understand it this way. So but so never mind. So let's say you have a trapezium. So this is A, length B, and this has a height H. So the formula to calculate the area of a trapezium is A over A plus B over 2 times H. So if you compare this to the velocity time graph, let's say you want to find the area of this region. So you notice that A and the B is basically U here and the V here, and the time is basically then the H is basically the time here. Since these two are right angles. Okay? Okay, so like this. So the last graph you need to know is the acceleration time graph. Due to space constraints, I'll not write the time thing there. So this is basically what it could look like. Okay, something like this. These are horizontal and vertical lines. Okay. 2, -3. So this could be how an acceleration time graph looks like. So what this means is the change in velocity over the change in time. So note that when the acceleration is negative, it doesn't necessarily mean the car is moving backward or whatever is moving backwards. It just means the motion of whatever object is requiring is slowing down. So the here the area under the graph is kind of like the velocity, or more technically the change in velocity from the time when t is 0. So it's like when t is 0 and when v equals 0 when t is 0, then the area under the graph is just the velocity. But if there's an initial velocity u, then you add whatever area that is later to the initial velocity. Yeah. So lastly I'll be explaining how to convert between the graphs. So let's say you want so there are two types of conversion. Um, you can convert um, displacement to velocity or velocity to acceleration. Second type is acceleration to velocity or velocity to uh, displacement. So first I'll look at the how to convert uh, velocity to acceleration. Uh, Displacement to velocity is basically the same thing. Let me erase this first. So how to convert from velocity to acceleration? So basically the thing you need to do is find out the different is to divide it. First, you divide the velocity time graph into regions with different gradients, since they're all different accelerations. Since here you have three regions: this region, this region, and this region. So um, so first, let's look at the first region. The first region, it travels in 2 seconds. The velocity has increased to 12 meters per second. So 12 divided by 2. So you take the gradient, 12 divided by 2 is basically 6 for the first 2 seconds. So yeah. So for the next for the next portion, this trapezium portion, you travel in 2 seconds, you have increased to 16 meters per second. So that the difference is 4 over 2. The gradient is 4 over 2, which is 2. So the graph will look something like this. Yeah, at 4 seconds. So in the last 4 seconds, the gradient is decreasing to 0. And so the gradient you find 4 seconds, 16 negative 16 meters per second. So you find the gradient is negative 4. Yeah, something like this. Okay. Okay, I'll just write it here. So this is negative 4. This is negative acceleration of negative 4. Okay, so this is when you convert this velocity time graph to this acceleration time graph. So the second type is converting velocity to displacement or acceleration to velocity. Let's choose velocity to displacement. Erase the graph again and draw a new one. Okay, so now I'll convert velocity time graph to displacement time graph. So to do this, the first step is to divide the velocity time graph into regions of equal velocity. So here there are three obvious regions. Um, three obvious regions. The first region is the region here. So the first region is in 4 seconds you accelerate for 4 you accelerate for 4 meter per second square. So what the graph would look like here would be something like this. Okay. This is 16 16 meters as the displacement. So next region, it decreases. So okay, so next region decreases by has a negative acceleration of 0 of um uh it has a of an acceleration of negative 1 for 2 seconds. So the graph would look something like this. 14 and displacement is 14. Use the area under the graph to see. Yeah. So then the last portion, it accelerates by 2 meter per second for um 2 meter per second for another 2 seconds. Wait, let me mark these two first. So the last portion will go something like this. 8 seconds. So displacement is let me extend this. Okay, 18. Yeah. So you have the three regions here, and you move them over here. So that's all for my video this time, and thank you and bye bye.